Hi everyone, my name is Eshkar. I'm from Yahoo Research. I'm very happy to be here, and in this talk I'm presenting a new feature we introduced in order to accelerate HBase in memory flash and compaction. This is a joint work of me with my colleagues Anastasia Borginsky and Eddie Bortnikov. So real-time content processing is becoming more and more of a requirement for businesses. If you attended today's keynote talk, this was emphasized there, and also if you take a look at the list of all the talks at this summit, you see that many of them are related to stream processing. So processing pipelines nowadays are used to in a broad set of use cases, spanning processing, stream processing, continuous computation, and parallelism of computed intense tasks. So pipelines, processing pipelines framework generally look like this. They ingest data, frequently often from multiple feeds, process the data in pipeline, and store the artifacts into the other artifact into a shared reliable storage like a key value store. So a prominent example is Sieve, the content management platform used in Yahoo for a search and personalization platform. And personalization product. It runs a pipeline of storm topologies on top of HBase. And in Sieve, HBase is used both for storing the intermediate results as well as to materialize the communication mechanism to communicate between different computation phases, which we call a notification. So notification, you can think of a notification messages mechanism like a sliding window. Producer agents write messages into the queue. Messages can be scheduled to be handled in the future. As new messages are written to the queue, the window expands, and the status of the messages in the queue can be updated. And as consumer agents handle the notification, they are removed from the queue and the window becomes small again. New messages are added, handled messages are removed, and so on and so forth. The main characteristic of these workloads are small working sets, where items have very short life cycles, and are frequently scanned in order to discover unhandled notification. In HBase, such high churn workloads of small working set means duplication. And HBase is not optimized for handling duplication in the data, and in a few minutes I will explain why. So our goal was to have a real-time performance and significantly less I/O in a persistent key value store. We achieve this by exploiting redundancies in the workload to eliminate duplicates while they're still in memory. We reduce the amount of files that are created, and thereby avoiding the amplification, the write amplification effect that is known to create network traffic and disk I/O. And finally, we reduce retrieval latency. It's important to note that the gain is proportional to the duplication level. The higher the churn is, the more duplicates we have in the data, the more the gain. But before I get into the details of our solution, let's take a step back and explain the HBase data model. HBase is a persistent map which supports atomic get and put operation and snapshot scans. A table is a sorted set of rows where each row is uniquely identified by a key. A table is horizontally partitioned into a sequence of rows by a range of key called regions. column family groups like data in a certain row. And a store implements a column family within a region. So store would be the focus of the rest of this talk. Finally, regions are assigned to nodes in the cluster called region server. Each region server can serve thousands of nodes, and which needs to share the resources of the node. This means that each per store allocation of resources is limited and is often very small and fixed. This assumption guides us in the design of our solution. So stores in key value stores are commonly implemented as log structure merge stores, which essentially transforms random I/O into sequential I/O. An LSM store organizes the data in a series of components of increasing size. The first component is an in-memory map, which contains the most recent data, and the rest of the components reside on disk. An important building block of an LSM tree or LSM store is a compaction or the merge procedure, which incorporates the content of one component into the next one. A core property of LSM stores is absorbing all updates into the memory and flushing them to disk when the memory is filled. This approach masks disk access latencies from the application and increases throughput since the I/O is it's performed sequential I/O. Now, write operation append a record at the write-ahead log for durability and add a new item or a new version of an existing item to the memory. Reads access both memory and disk component, and when the workload is skewed with high locality, they hit the cache most of the time. Finally, periodically, merge or compaction procedure eliminate duplicate version and tombstone, which are used to mark deleted items. Okay, so this is a picture of general log structure merge store. It is implemented in HBase, but also in many other key value stores like LevelDB, Bigtable, and others. Now, this is how the HBase stores looks like. These components are actually HDFS files, which means whenever a new file is created, it is replicated across the cluster. Now, a write operation writes the item into the memory component and adds a record to the wall. After the memory component exceeds a certain threshold, the data is flashed to disk. So first, the active segment becomes immutable, and a new active segment becomes available to absorb new records. And then the snapshot segment is flashed to disk, then some records in the wall can be truncated, no longer required. And at the background, we have disk compaction, which takes few files and rewrites them after merging them rewrite them back to the HDFS file system. A read operation in HBase accesses both the active segment as well as the snapshot segment, and also the files on disk. And when the dataset is small enough, it may find it in the cache. In HBase, the application level cache is called block cache. But when the data becomes bigger and cannot fit into the block cache, the heat ratio drops and the reads become slower. So here the compaction comes to help. When compaction picks a few small files, and compact them into fewer bigger files. This means that the data now may fit into the cache, and the heat ratio goes up and the reads are boosted. But on the flip side, we know that writes are known to be amplified, which means that every write of a new file causes replication-related network and disk I/O. So to reflect back on what happens in a high churn workload, we have, in a very short period of time, we have items that are added to the store and updated and then removed from the stores. This means that each item has multiple versions, and the data most of the time cannot fit into the memory, and therefore it is flushed to the disk, even though the working set is very small and could have potentially fit into the memory. So if we summarize what we saw so far with the default implementation in HBase, is that it either suffers the penalty of an I/O, the I/O penalty, or it needs to pay the price of high latency in reads. So here comes our new design for in-memory flush and compaction. The solution is very straightforward. We add a compaction pipeline between the active segment and the snapshot segment. When the active segment is filled, it is flushed into the compaction pipeline. There, the segments are being compacted in memory. When the heap that was allocated to the mem store is exhausted, the last segment in the pipeline is flushed to disk, and making more space for new updates to come in. So note that this means that we also had to refine the while truncation protocol to adjust to the new solution. So one way to look at the new solution is to see that it trades smaller read cache for larger or bigger read-write cache, or that it trades much more CPU cycles for less I/O. Okay, and these two observations have caused us to evaluate the new solution in two main settings. The first one is when the data can fit into the memory. So we've used YCSB framework to compare the compacting design versus the default implementation. We used a small cluster with 3 HDFS nodes and 1 region server. We allocated 1 gigabyte space for the region, and we used a local allocation buffer to avoid the garbage collection effect. Now, we allocated the same amount of memory for both default and compacting implementation, but we split it differently. The default implementation used a smaller write cache and a bigger read cache, while the compacting memstore used a bigger write cache and a smaller read cache. And we evaluated a high churn workload. We used 10 threads to run 5 million operation in various, selecting the keys with various distribution. We started by exploring a single atomic operation. We evaluated the 50% reads and 50% update with a target of 1,000 operations per second. Then we also evaluated long scans, which were the size of a scan were selected from a Zipian distribution with the maximal size set to 20,000. So note that while the portion of the scans is very small with respect to updates, since they are so long, most of the time, actually, the scans spend more time than the updates in the experiment. Finally, we measured the average latency over time, which means that we can see the dynamic behavior of the system over time. And this is what we get for the first setting that I've just described, where the memory can potentially fit into, where the data can potentially fit into memory. So what we see that the blue line represents the compacting implementation, and the red line represents the default implementation. What we can see that the two implementations start at the same latency because they are both serving the reads from memory. And since the compacting design continuously compact the data in memory, it continues to perform, the performance continues to be flat throughout the experiment. The default implementation, however, behaves differently. So the purple dots represent the flush event to the disk, and the blue or light blue dots represent the compaction event to the disk. So you can note that after the first flush to the disk, the data still fits into the cache. Therefore, the latency is still very low. But as of the second flush in the original implementation, the data no longer fits into the read cache, and we can see that the latency now deteriorates. The compaction helps to reduce the latency, but then again, when we flush again, it goes up, and so on, and you can see how it behaves for a long time. For a uniform distribution, we see similar behavior, just that at some point at the fifth flush, there was a region split, triggered a region split, so now it takes more time for the memory to flush, and then more time for the memory to be compacted on the disk. Here we can see the results for the scan. Obviously, they're much more noisier since the size of the scan is not fixed. So it's somewhat hard to see the results, but you can see that the behavior, the trends are more or less similar to what we've seen with the read and write operation, with the read and write experiment. Next, we try to evaluate the case where the data cannot fit into memory. And specifically, we added the delete operation, which used tombstone. Now, tombstones are not compacted as part of an in-memory compaction. Therefore, at some point, the data, also in our design, has to be flushed to disk. So I've highlighted the main differences between the first experiment and the second experiment. So this time we had the same amount of size for both the original implementation and the compacting memstar. The difference is that in the minimal size of files that we required for triggering a compaction. So for the default, we had a minimum of 4 files, and for compaction, we had a minimum of 2 files. Now, as you will see in a minute, still the default implementation does a lot more compaction and a lot more flushes than our design. We added delete operations, and we gave a head start to the updates of about 50,000 operation before we started deleting items that are in the store. Okay, so here you can see that we don't have a flat line in the compacting memstar, because at some point data does go down to the disk. But what you can see is that while we had a total of 2 flushes and 1 disk compaction, the original default implementation had a total of 15 flushes and 4 disk compaction. And I remind you that every such flush and compaction writes data to HDFS, which means a lot of replication and a lot of load that is added to the system. So this was the previous slide was for zip-fin distribution, and this slide is for uniform distribution. Again, we can see the same trend, the same behavior, just that this time the compacting memster had a total of 3 flushes and 2 disk compaction, and the default implementation had the same amount of flushes and disk compaction. And finally, this is the scan latency. Again, a bit hard to see, but if you do see, then you can note that it, again, have the same behavior as in the read-write experiment with deletes. So while we could have, and we are pleased with the results, it's still important to note, as I said in one of the first slides, is that actually the gain is proportional to the duplication. So if we have a workload that has almost no duplication, then we don't see any gain. So what we've noticed is that actually that the new design is also can be a platform that enables us to apply some memory optimization that could actually help improve the performance of HBase also in the general case. So I'll just touch upon it because this is still a work in progress. So the current design, actually the data stored in flat buffers, namely the keys and values themselves are stored in flat buffers. However, the index is a skip list, simply Java skip list. And all memory is allocated on heap by default. Now that we have immutable, we have multiple segments in the memory component that are immutable and are actually when they're written, we know how many items are going to be in the segment. We can simply implement the index as an array and just use binary search to efficiently find keys in the segment. So we can use the flat layout for the immutable segment index. And now that all the data is flat, it should be fairly easy to manage the data buffers of heap. And that should obviously help us get more boost in the performance. So the advantage of the memory optimization is that we'll have locality in access to index, will reduce the memory fragmentation, which obviously will reduce the garbage collection work, and we'll have better utilization of memory and CPU. The status of the project is currently as follows. We have an umbrella JIRA that has several subtasks, 3 of them which involve major infrastructure refactoring of the core memster building blocks is already committed. The JIRA that introduces the new compacting memster is now in advanced stages, and we hope it will be committed very soon. And finally, the memory optimization subtask is still work in progress, and it's under the code review of the community. So to summarize, we've introduced a feature that we hope it would be integrated into HBase 2. The advantages of the new design over the default implementation is that it has predictable retrieval latency by serving the reads mainly from memory. Less compaction on disk reduces write amplification, which in turn should improve the overall utilization of the system and reduce the load on the HDFS, the underlying HDFS. That's it. I just want to thank the reviewers, Michael Stack, Anup Sam John, Ramkrishna Vasudevan, and Tedu. That's it.
are you just increasing the mem store size for this to handle the compaction, and are you able to isolate that piece of the mem store for that? Because these are minor compactions, right? They're not major, because you said these are still tombstone.
Yeah, this is currently, this is equivalent to minor compaction because, so for those who are not familiar, minor compaction, difference between minor compaction and major compaction is that if you just do compaction on the set of subset of the files, you don't know if you can get rid of the tombstone because they may be needed to delete other items that appear in different files. This is exactly the same case when we are in memory. We don't know if there are items in disk, so we cannot remove the tombstone. But you can think of a way to have the Bloom filters that would represent the set of items that you have on disk. So if you somehow can know for sure that the item does not reside on disk, you can eventually get rid of the tombstone in memory. But I don't think this was the main question you asked.
Now the part of it, so the second piece is, how are you isolating that compaction within the mem store? Are you allocating, is this a new configuration?
No, so as I said, the three first subtasks were actually to refactor the mem store. So the default mem store had it was kind of a mess, and now you have an active segment and a snapshot segment. So the segment is like a first citizen, it's a new entity, first citizen entity, and now you have a segment, so now you can have a pipeline. You have segments in the pipeline.
So how does that, so final question, stop, take. How does that work with the HA read? Because if the HA reads,
what do you mean by HA reads?
High availability reads on HBase.
Okay.
So how does this work with HA reads?
I'm not familiar with the term, so I don't know exactly what you mean by.
So high availability reads are not available in HBase, right? So if this is doing.
Why do you say that? You have the WAL, you have
so it's a replication factor on the other regions.
Okay.
So the master basically publishes the regions on other nodes.
You mean that you can't read from the other replicas. You can't just read from wherever you want. You need to go through the region. This is what you mean? It's not high available?
No, I'm just curious how this impacts high availability reads on HBase.
So as I said, I'm not familiar with this. So maybe we can take it offline and then we can discuss this. Yes.
Does it play well with the bucket cache? I mean, the off-heap cache?
We haven't tried it with the off-heap cache. We just the experiment used. I think the default is the LRU cache, so we haven't experimented. But what would you think that it should work better or worse? I mean, it's orthogonal.
You said the block cache would be probably a bit tinier.
No, this was one configuration that we experimented with, but the other experiment was that they had exactly the same size. So, I mean, you can think of it as, I'm not going to go down to the disk as frequently as I was before, so maybe I can use just a smaller cache, but you can think of it the other way around. Yeah.
Some point it has to flush. Does it just
No, so I showed in the second experiment that I show the case that where we do flush. So, but even when we we delay. We can say that we delay the flush. So if you can configure the system in such a way that says, okay, so if you're going to flush not so frequently, you can maybe you can do the compaction more frequently. Or you need the minimum number of.
I guess my question is there a fixed size? Like even if you do these compactions over time, you will exhaust the memory that you have.
Definitely. This could be a case.
Or is that kind of basically once you get to your mem store, your recently written memory cache
It's configurable. So the administrator sets the size of the mem store, and we just play by it. We just try to make the best out of the memory that was allocated to us. And as I said a few times, if there is a potential to gain something, we gain it. Yeah.
So obviously your stats are all on the 50th percentile mean between the frameworks?
It was where is yeah, it was the it was accumulated on 10 seconds.
Yeah, so 10 seconds, 50 percentile means.
Yeah.
So do you have any stats about the fat tails and the improvements it's brought to?
Yeah. So I think that by showing this behavior, I mean, if I just told you that we reduced the median by a factor of, I don't know, x, then this would be a good question. But actually, now that I'm showing you the dynamic over time, I mean, what would be the percentile of this? If you look, so the average is about here, and the 99 percentile would be this. So I think what we present is more detail. You can see in your eyes and understand exactly what causes the percentile. So the answer is I don't have the results, but I think that this shows the detailed picture, and for us this was enough. But it could be interesting also to look at the granularity of the buckets, to look at the percentiles. But I don't think we'll find something that's more than we can see here.
I think you might find actually you've got a great big improvement on your fat tail, if anything.
I think you can see it here. Yeah, definitely. I think that it's not like I'm just telling you we have an improvement on the fat tail, but I'm showing you exactly how and when you can see it. Yeah, definitely. Yeah.
Which type of garbage collection do you recommend for using for HBase?
I don't think I'm the right person to ask, actually.
What was the question?
Which garbage collection to use? Maybe John, you know.
So I think we generally would recommend G1 GC up to about 96 to maybe 128 gigs of RAM. If you're going to use the traditional Java 7, Java 6, RNU, and concurrent market suite, you probably, if you care about latency, like if you were to use this potentially, probably 16 to 24 gigs.
Yeah.
You have to increase the size of the hidden space because the objects are staying in memory long time, so it might be promoted to.
We haven't tried to I don't know somehow to configure the garbage collection, but obviously if you want to further drill down on this, but if we take the entire data, at least the immutable data of heap, so the entire question about garbage collection becomes irrelevant. Thank you.